We're going to be talking about the spooky world of quantum, which is undoubtedly one of my favorite subjects. And to help us understand this, we're joined by two great experts. And Heike, I wondered if I could start with you, if you could help us understand this world. I think it's fair to say that quantum is having a moment right now. Last year, we saw that the shares of the 4 listed pure quantum companies in the US rocketed and then fell back a bit by the end of the year. We saw a lot of quantum startups raising very significant amounts of money. And a lot of people are making some big claims about quantum right now, and the timelines of deploying a kind of commercially valuable and viable computer are shortening, I think. And people are beginning to talk about using it in a very significant way. But there are also a lot of zombie claims out there as well, to use the terminology of Scott Aronson, who follows this very closely. So help us out here, Heike. Tell us, what is the hype and reality of quantum at the moment? Why is there such excitement right now? And to what extent is it justified?
Yeah, quantum computing, as you all know, right? It's a totally new technology. There's lots of activity. There's also lots of investment going on. And over the last 10 years, a lot of progress has been made. And we are at a stage where we are right at the cross-section of demonstrating true quantum advantage. And quantum advantage we define as a true advantage, commercial advantage, where you can calculate a problem more accurately or faster, or also at less energy. And I think all these are very important components from an economic value, and of course for a problem which is also of economic value. We have seen calculations of quantum computers where things have been demonstrated which a classical machine cannot do, but they were scientifically very interesting, but economically irrelevant, right? And so in order to, of course, everywhere where there's new technology, whether this was in nanoscience or in carbon nanotubes or other things, there's always also hype connected with it, because people also sometimes only use the terms for selling something they want to sell. So we actually did already in 2020 start with putting together a roadmap. A roadmap which tells, and we share with the world, of what are we going to demonstrate in the coming years from a hardware point of view. How do we increase the performance, which means number of qubits, plus quality, and plus speed of how fast you get the result. On the other hand, also software stack needs to be built up, that people can also very easily use quantum computers in the future, that there are the corresponding functionalities implemented and everything, and where you clearly see when things are coming up. And the important piece is not only that we built this roadmap, but that we every year we made our check marks that what we promised we also delivered. And I think this is very, very important for a new technology, that because this creates trust, right? If you see in this new technology there's a promise, you can understand how the progress is. You can also plan your own endeavor for when the technology is ready and start using it, etc. And then having these check marks gives a lot of trust. So we have, but we have extended this roadmap also, and I think now we are really, as I said, at this edge to demonstrate quantum advantage.
Right. Can you give us some examples of the kinds of problems that quantum computers can tackle that we can't with classical computers?
Yes, so up front, a quantum computer should not replace all classical computers, but it's actually a tool which can calculate problems which classical computers are not good in. And I give you a very simple example, which is if you do multiplication, that's very easy, right? Even big numbers you can do on paper. Some of you perhaps even in your mind, but some of you on paper. But if I give you the inverse and they, okay, this is a huge number, now give me the prime factors, do the factorization. Then it's very, very hard. And even a classical computer needs a lifetime to do it. But there are quantum algorithms who use the strange phenomena of quantum physics, like superposition, entanglement, and interference, where with these new capabilities which quantum physics gives us, this problem can actually be solved in only a few minutes or a few hours, right? When we have a fully corrected quantum computer.
And that's obviously massively important for the world of cryptography, isn't it? Because most of our current RSA encryption methods are based on
That's
technology
right.
which can be cracked by quantum computing.
So that's when Professor Shor from MIT actually published this algorithm in 1994. We started actually already then, although quantum computers, the reality of it was still far ahead, to do theory and develop new algorithms for encryption. And so we come a bit to the other topic, but these are classical algorithms, no quantum algorithms, which can be used for encrypting the data. And these classical algorithms cannot be faster calculated by quantum computers than classical computers. And this is actually where the world is switching to. There have been lots of reports also from all the different governments to advise and recommend when companies should be ready, and actually you should start already now to encrypt the most important data you have, and which should stay for a long time encrypted with these new algorithms, because people can harvest already now the data and later decrypt it.
Yeah, I'd like to come back to that in just a minute. Victoria, at E.ON, you're responsible for a range of kind of technological innovation. How large does quantum loom at the moment, and how are you beginning to apply it?
Yeah, perhaps first, I mean, E.ON is the biggest European grid distributor. So actually, for us, digitalization is the one big important thing, in addition to getting power lines to the right places and connect them. And digitalization has a lot of different components which are relevant. Clearly, the last couple of years, Gen AI has been a very big component, good data estates, etc. And if you look into all of that, actually, quantum would be like 0.01%. And if I look into my job, I would say it's my hobby. But I think it is a very important hobby, and this is why we are doing it, and this is also why we think it is relevant for our business. And it has two aspects. The one aspect is, like Heike was saying, you need very complex, multifaceted, multivariable problems which might even be nonlinear. And then quantum computers help. So we have this problem because the energy infrastructure in Europe is changing completely. It's changing from a centralized power supply to a relatively well-predictable power demand towards decentral, volatile, nonlinear, non-deterministic problem with both on the supply and the demand side. How can I predict who of you is now loading their electric vehicles here, or do you load them at home? And if you put this into math, it's as difficult as Heike's problems. So quantum computing, actually, a nice problem for quantum computing is actually really electric vehicles in Munich. What is their charging pattern in correlation to the weather, football games, temperature, etc.? Because this is all relevant for the power supply in Munich, because you still want to drive your car. If you ask this to a classical computer with all the nice Gen AI stuff we have, the computer takes longer to calculate than you would need your electric vehicle. So the only way to really answer that, the only way to have the right models on classical computers to make sure we have the right power supply in place, and we still can pay for it, is quantum computing. And this is why we run the first examples on stuff like that, and we actually succeeded in having two answers which help us for classical modeling. And this is very relevant not just for the power supply, but also if you look, a lot of you probably profit from the economic upturn we see in the US and also in Europe, because there's a lot of data center capacity needed. If you look at all the problems Gen AI wants to solve, this is crazy. This is costing enormous amounts of money. Quantum computing, if applied for the right problems, is going to save us a lot of money for energy and for infrastructure. And these are the two reasons why we look into it. And again, I think you said it, now it's the age of quantum. I think we're at the brink of something, and we have the first results, which is much more than can be said for a lot of other technologies. So I think it's promising, and we are lucky that we have the right problems to be addressed with it.
And how practically are you going about it at E.ON? How are you building up your expertise in this area? How are you building a team of people who can understand what the possibilities of using this technology are and to what problems they can be applied to?
I think it's kind of a three-level problem. I think the first level is digitalization, good data estates, a good understanding of where you use digital in physical infrastructures. And this is what we do. I mean, this is one of this at the core of our company. The second level is then to understand which technology should be used for which problem, or how can you generate new business opportunities by using a technology. And then the third layer is to have the right interface, and for Gen AI, you would say prompting ability, to say, hey, this technology is the right one and I know how to use it. And for this, we have a very small team working very closely with some universities and with IBM to build the skill, because from a business perspective, I trust all these great scientists to build the quantum computer. So that's all nice. Doesn't help you if you are not able to ask the right questions. So what we built in our very small team, we built the ability to translate a business question into something which can be usefully answered by a quantum computer. And this is a little bit the same skill as you would need for complex LLMs, where you also need to have the ability to phrase the right question or to build the right, on top, small language model to operate the large language model. And I think that's something we train, but it's 3 levels, and the expertise for quantum computing, it's very few people, and I also think this is enough.
Right. And I'm interested that European governments have for a long time been investing heavily in quantum. A lot of quantum research has gone on in Europe and so on. To what extent is this an area where Europe does have an edge at the moment, and to what extent can it be sustained? Heike?
Oh, there's as you said, there's a history of excellent quantum science. Actually, the term quantum physics was termed in Göttingen, etc., with great scientists. And there is also a transition going on now from having startups which have been created. I mean, here in Munich, we have the Munich Quantum Valley, which invested also a lot and has lots of startups which are also making their progress very nicely. Also, not only on the hardware side, but I have to say also on the application side, because I think Victoria mentioned it already, the application space is a much bigger space, right? And we talked about optimization problems, which you said, and by the way, they're not only at E.ON, they are appearing actually everywhere, even if you have a fleet, or if you want to schedule your manufacturing, and many other optimization problems benefit in the future from quantum computing. And also in the chemistry and material science. So there is lots of activity also on the application side. And I think this is something where I see a bit of a gap, that we are also having more expertise and activity and algorithm development on the algorithm side, because in the end you have a tool, right? And this tool you can also combine with a classical machine, with an AI machine, and this is actually the future, that you have a big problem you want to solve, and a part of the problem you may solve with AI, and a part of the problem you solve with quantum, and how you also disentangled it, right, is important for having expertise to do this, in particular in the next couple of years. Of course, in 10 years, right, perhaps you only work with libraries and you don't need to know how it really works, and you don't need to have the insight which your team now has. But in the early phase of using the economic value of quantum, it's really important also that you have a team who understands your own business, where you can add value with solving more complex problems which you can't do classically.
You were talking earlier about the kind of pathway that you have at IBM as well. When is your best guess about when IBM will have achieved quantum advantage?
So actually, it's on our mission for this year to achieve quantum advantage, not for all the problems, but for specific problems, because we have improved our hardware, that we can run many iterations, gate operations, and that we have reduced the error, that we have techniques to mitigate the error which still appears in quantum bits. And we are now at a stage that the hardware provides quite a lot of capabilities for a specific problem to be solved. This is to be demonstrated this year, so we are working very energetically on this. And then the next big milestone is actually where we, of course, already also work on bringing all the components together, is to demonstrate in 2029 the first fault-tolerant quantum computer with 200 logical qubits, who can run more than 100 million of gate operations. And for this, the complexity of the problem we can solve increases by a factor of 20,000 compared to today.
Give us an example. What would you then be able to solve at the end of 29 that you can't solve today?
So we are actually today, if you look at molecules, right, we are actually today already looking into smaller molecules. So this may be silver sulfide particles, which play also a role in catalysis. And then we can increase the size of the molecule dramatically. Today you can still calculate these silver sulfide clusters with the combination of HPC and quantum. And in future, these problems explode then, right? So you can, actually we have a health track here next to it, right? So then making predictions on the properties of molecules and also predicting molecules with certain properties is something which will then become realistic.
It's going to be quite a moment, isn't it? It'll be quite fun when that happens. Victoria, could I come back to the issue of kind of encryption? A lot of companies, particularly in the finance sector and digital economy, are working very heavily on the post-quantum encryption world. How worried are you at E.ON about the threat that Q-Day, as it's called, might pose to the security of your data? And how are you anticipating that?
Well, I think first, we always talk about new technologies. I think when I grew up, I met people from secret services who told me they're investing into quantum research because they fear quantum cryptography. And this was in the 80s. So now we have 26. Still nothing big breached by quantum cryptography. Outstanding Gen AI capabilities. And like we're a company, like we're super pragmatic. So we deal with the stuff we have. Actually being an energy company, we deal with physical terror attacks. And that's what we do. I mean, like in Europe, we have quite a few of them. Very unpleasant if you don't have power in your home because somebody thought it's nice to burn the power supply. So that's the first threat. And then we have a lot of nations who are super active in trying to breach whatever cyber which is possible. They're really good at it. There's a lot of Gen AI and AI around, and we try to protect ourselves. And if something new comes around, we kind of a little bit are close to this quantum stuff, so probably we will be with the first 10%. And we will try our best, but I don't think, like we are not, actually, our assets are in the ground. If you want to destroy them, and that's shown by terrorists, if you want to protect against this, you need a good police force, you need to have a good society which actually protects what they invested in. And crypto is, it's on a big list, but on top of this list, even from a digital perspective, would be cyber attacks driven by Gen AI, nation states, targeted attacks, and stuff like that.
Yeah, okay. Some people are talking about the concerns about the store now, decrypt later phenomenon where an adversary would kind of harvest a lot of data, even though they can't decrypt it now, but once a quantum computer sufficiently robust enough to do this would then be able to decrypt the data. What do you think, Heike? Would you be advising companies to think about this post-quantum world now and prepare for it?
Yes, I want to perhaps refer also to Victoria, what she said about putting in perspective of how quantum has developed. When I studied quantum, physics, and you also studied physics, right? Quantum computing was like a theory, right? We learned the theory, and we did not believe that this will come in our lifetime, kind of, right? But it took like 20 years to do all this theoretical understanding of how a quantum computer needs to work. And then it took like 15 years for the experimental quantum physicists to actually build qubits and understand the physics, how to control the quantum physics, how to control qubits, how do you make them interact, how to reduce the error, how to increase the coherence time from nanoseconds to milliseconds, right? These are 6 orders of magnitudes which have been changed over the last 15 years. And since like 10 years, where we started with 5 qubits, now we have chips with more than 1,000 qubits on one intrinsics, and this technology development has been done the last 10 years. Algorithm development has been done, where we always thought things which we predicted actually moved closer. And the same is actually true for the decryption using quantum computers. Because as soon as you have fault-tolerant quantum computers and you have a modular path as is developed to scale it up, the engineering, it's engineering. It's no longer solving hard physics problems where you can't predict the outcome. It's really more going into an engineering problem where you can better predict when the machine will be there, that you can do it. On the other hand, if you look in the algorithm for decryption, also there, smart guys have made lots of progress, and you can believe that there are many people working on it. And so there are also there, the number of logical qubits you need for the algorithm to work is also going down. So therefore, these things come closer, and this is why there is a reason why the Bundesamt für Sicherheit or the France, UK, USA, etc., they have all made reports, and they tell their administration that by 2030, you now have to get a strategy. By 2030, you have to have encrypted the first batch of data in the secure way, and by 2035, all data should be encrypted in this way.
Yeah.
And
Of course, Victoria.
from a science perspective, I completely agree. It's just from a business perspective, you also need to earn money, and I like my pledge for quantum, and we have great technology. I agree on all the progress, but we need to create something new. And quantum cryptography is always this ghost which comes when you need to explain whether you spend money on it. And I would love to replace ghost with living business. And yes, we need to do that. I agree. It's something like, yes, we do it. But the cool thing is if we create value. And there's stuff where we can really create value. And this is why I'm so much, but yes, we need, I agree, it's nice, and it's probably going to earn IBM money. But from a like pragmatic business perspective, let's go to the things which really create a difference. What if I can save 10% of grid capacity which I need to build out because I use a quantum computer? That's a big difference, because people have faster connections, we can connect renewables faster, we have less energy which just goes to waste. That's a big impact which is visible for everybody, not just for a very small society. And this is why I'm pushing so much.
Yeah. I don't mean quantum cryptography, so in the sense of quantum communication. Is this what you... Because that's not what I mean. Because there are people
I think we're probably going to have to take that discussion off stage.
Sure, happy to do though. But there is a big difference between quantum communication, quantum safe communication, and encrypting data with a different classical algorithm, which is already implemented actually in many storage products you can buy.
Anyone who wants to understand more about that, please contact
Come here.
Victoria and Heike. But thank you very much for a fascinating discussion.
Thank you very much. Thank you.